Oh well, we start with a blank screen, but only for 1 second. Okay, good. So today we're going to pick up on causal Gaussian models, okay, and particularly the AR model we're going to talk about. And you've been reading. Okay, so you've read the notes. You've been reading the notes, right? So you're supposed to have read through section 323. Did everybody read it? See, it seems a little sparse out there. Okay. And what about the, I got some emails, I'm trying to get through the emails and people asking me questions about the homework, okay? Actually, the homework questions I've gotten have been pretty good. I mean, they've indicated that people have a pretty clear understanding of what they've done. So, are there any questions? I can actually answer some questions. If, sometimes, usually if someone here has a question, people are aware of it, okay? So, no? No? Are you okay? So, yeah. So let me switch over, I guess, to the document camera, okay? And we can kind of get started from that. Okay. Now, so we talked about last time. I'm kind of going through the notes again. We talked through last time about causal prediction, right? And so you have the concept of the past, of the future, the past, and the present, okay? That depends on having a causal order of the point. In one view, that's pretty straightforward. And then you can predict the current point from the past point using the conditional expectation. The conditional expectation is the minimum mean square error predictor. For any distribution, it minimizes the mean square error. In the particular case of a Gaussian distribution, you know that this conditional expectation is going to be a linear function of its argument. Okay. So what does that mean? The conditional expectation of y given x, right, is a random variable. It's really just a function of x, a random variable x, okay? And if x and y are jointly Gaussian, what do you know about this function of x? What form does it have to have? Excuse me? Linear, thank you. So it's going to have the form ax plus b, okay? If it's a vector, all right? In general, is it going to have a linear form for any random variables with any distribution? No. Because if they're not Gaussian, it generally would be nonlinear, right? But what do you know about the conditional expectation? It's always going to minimize what metric of error? Mean square. Mean square, okay? Okay, good. So this will minimize the mean square error, okay? So right now we're considering Gaussian. We're going to start with Gaussian distributions, but in general, this would always be the conditional expectation is the minimum mean square error estimate. We're using all the previous information. We're estimating the minimum mean square error estimate is the next value, okay? And then we can take the difference. The difference is the error, right? Now the thing that's really interesting, and it's really not too hard to prove, is that, well, first of all, if this is a Gaussian random, if they're Gaussian random variables, then this conditional expectation is going to be a linear function x. And if, well, okay, technically this is not a linear function, right? Do people know that? This is an affine function, okay? Because for it to be linear, b has to be 0. It's kind of a detail, but it's an important detail. Well, depending upon, if you use this linearity in theorems, okay, it really actually has to be like that, okay? So, but if we subtract off the mean, if x and y both are 0 mean, then it'll be just linear, okay? So if it's either 0 mean, so if x and y are 0 mean, for a 0 mean Gaussian random variable, random process is a linear function of the path, okay? That's a linear function of the path, and the error here, okay, is it's then going to be a linear function of the path too, right? Now, what's kind of interesting, there's a few things that are interesting here, okay? One thing that's interesting is if I look at this if I look at that expression, I'm only summing over the past value of x, right? So if I set it up as an equation, x is a vector, right? Okay. So this is x, okay? And then it gets multiplied by a matrix, right? And the result of that multiplication of that matrix is an output, which is a vector. And that vector is what we're going to call epsilon n. That's epsilon. So if I put the n down here, it just emphasizes it's a function of n, right? And this index here is n. And n starts at 0 and goes to whatever the maximum value is, or n here. I guess I should use an I. Okay. Okay. Now, so this is x. Do I start at 0? I'm sorry, x1. I start at 1. Okay, and then this is xn. Okay? And then this is epsilon 1, and this is epsilon n, right? Now, the error at a particular time is the difference between the current value of x and the previous values, right? So it's going to be this. I take the current value and I subtract the previous value. So I'm always going to, yeah?
The current value of x minus a linear function of the previous value?
Yes. Right, yeah. I'm sorry. Yeah, minus not all, yeah. I'm being a little loose in my speech. Okay. A linear operation of the previous one. Okay? So you're always going to have at least the current value, right? So there will be ones on the diagonal. Does everybody see that? Will be ones on the diagonal. Okay, now you won't use the future value, right? So for a particular value here, say epsilon I, and this is xi, right? You won't use the future values of x, right? So these all have to be 0 there. And then along here, you're going to use these things here are going to be the values of h that, these are going to be weights, okay? Those weights right there. So this will be HNI. Okay, that's that matrix HNI. And actually, it's not HNI, it's HNI times minus 1 because you're subtracting. Because this operator times that produces the predictor, right? And then you put, now the predictor doesn't use the current value. If it did, it could cheat and always get a perfect answer. So it always has to be strictly lowered, triangular, but then when you add the current value, you get a 1 on the diagonal. So this whole thing here is a linear operator, which is lower triangular. And hold on for a second. Okay, that's what I guess I'm calling A. Okay, so this whole thing here is in a node called A. And A then has 1s with a diagonal, 0s above the diagonal, and is the minus 8 values below the diagonal. Okay. So what's the determinant of that? It's got to be 1, right? Because of the 1 from the diagonal. And for a lower triangular matrix, it determines the product of the diagonal elements. Okay, so now, and also H here is just this matrix here, written out in more detail. Okay, so A here is really equal to the identity matrix minus H. All right. Actually, the determinant of H is 0 because it has all zeros on the diagonal. Okay, so it's important to be able to see that this can be viewed as a matrix operator. Okay, so we're going to do this a lot. As a matter of fact, very often these operators will get used, and in practice you wouldn't actually use them in MATLAB, but conceptually they're very useful, right? So epsilon here is going to be equal to I minus H times X, and that's going to be equal to A times X. Okay? Now, okay. Now, one thing that's really interesting is that you can prove, hold on. Playtech is very clever. It doesn't number all my pages. Okay, I've lost track of where my pages are. Here, this is 3 points. Hold on for just a second. Gotta be careful. Okay, 36, 37. Okay. So, okay. One thing you can do is you can prove. Right. You can prove that you can look at the correlation of. You can prove that the correlation of the input of xi with the errors. Okay. You can go through this argument. Okay. You should go through this argument very carefully because the steps in it are very useful. I mean, I guess I could go through it really fast. I'm not sure how helpful it is for me to go through this, but okay. So if I can stand epsilon out as x minus x hat, because that's its definition, and then I can use the associative properties to write out these products, right? Now, expectation of a sum, expectation is linear, so I can always take the expectation in two resulting terms, right? Now, then this is sort of a clever thing I can do. So I can, xn hat is the prediction value for time n. So that's defined as the conditional expectation is xn given f of n, where f of n is the past information, okay? It's just shorthand notation for the past information. So now, the past information includes I, because without loss of generality here, I assume that I was less than n, okay? Now, if I is, okay, right, okay, no, it's not without loss of generality, it's, okay, I have to assume I is less than n. I'm showing that xi is uncorrelated from the previous, prediction errors, right? And then, so xi here is is basically a constant because this is the what's inside a jar of peanut butter issue. Because fn is the past and xi is something in the past, so the conditional, so the value of xi given the past is known. So I can take this inside and out of that expectation. It's essentially a constant given x of n. Does that make sense? All right. That's what I think I call the filtration property. So then I take that inside, okay? Now what I can do is I say, oh, well, if I take the expected value of a conditional expectation, well, it's just the expectation. That's one of the other properties. See, this is where you use these simple little properties and you manipulate them like a Rubik's Cube, okay? And you can get sort of clever, unintuitive results by a sequence of these little manipulations, right? Actually, this is one of my favorite things to do. Okay. Yeah. So then you have now these two terms are the same, so that's zero. So I've shown through a basic principle, a very basic, rigorous proof, really, that xi has to be uncorrelated from the current prediction error.
Can you please explain how you got xn hat?
Xn hat is defined, okay?
So how is it expectation of xn given fn?
Okay, because that's its definition. Because that's the minimum. I started off by saying that xn hat is going to be the minimum mean square error prediction of the current value. So the concept here is that we're going to model a random process by being able to predict it. I mean, I haven't shown that yet, but we're going to show it, okay? So it's a Gaussian random process. In regard to whether it's Gaussian or not, this conditional expectation would be the minimum mean square error predictor, okay? So, okay, does everybody follow that? So that's the definition, but this is the proof, okay? Now what I can do is I can actually show that, so the epsilon n are independent of all the past values. I just stated that here, okay? Okay, now, this is a really clever little thing here. I'll go through this real fast, too. Now I can show that the prediction errors are uncorrelated. They're all zero mean because I've assumed that everything's zero mean, okay?
That's just without loss of generality.
But the expected value of epsilon n times x epsilon I, now we're going to assume that epsilon n is not equal to epsilon I. So without loss of generality, I can assume I is less than n. If n was less than I, you know, it'd be exactly the same argument I just reversed. I mean, multiplication is commutative, so I could just flip it.
Right. By symmetry, it's up to
Now, so now I just expand out the definitions of those two things.
Okay, so this is the definition of epsilon n, and here I just plug in the definition
of the conditional expectation of x hat of n. And now I start doing some sort of interesting manipulations. I condition this whole thing on Fn. I can do that, so I can, if I, you know, one of our properties was that the expectation, you know, the expectation of y is got to be equal to the conditional expectation of y given x, and then I take the expectation of that whole term, right? So the expectation of y is equal to the expectation of the conditional expectation of y given x. Okay. So I can use that sort of relationship to my advantage, so I condition on this thing on the inside. And I condition on Fn, which is the path before n, and I is less than n. So if I is less than n, that means that this term, xi minus
so the conditional expectation of xi given fi, that's a constant given fn.
So I can take that out of the expectation.
Right.
Now, the conditional expectation is a linear operator, so that if I have conditioned twice with respect to fn, it's the same thing as conditioning once. So I get the same two terms. But since those are equal, then they're almost surely equal to 0, and then the expected value of that whole thing is 0. It's kind of a, I just like these proofs because they're very elegant, right? It all depends on what you like anyway. I really like this. Okay? I just think it's so cool.
Powerful result. It's these simple little manipulations, right?
And it's very fundamental, okay? If you start doing the integrals of the density functions, you're making a lot of assumptions. This is always true, okay? So, it always has to be properly interpreted. I mean, the expectations have to exist. But the expectations always exist for any positive random variable, or the only time an expectation doesn't exist is if the positive and negative part of a random variable are both an expectation which is infinite, okay? But if it's a Gaussian random variable, of course they can have it. Okay, all right, good. So now what we've shown is that the prediction errors are uncorrelated, but if they're uncorrelated and they're Gaussian, they have to be independent. So the prediction errors are independent, okay? So that's really interesting. It says that if you have a random process, and I'm drawing a random process, like little circles, and then you take the path, and you predict it, and you subtract it from the current value, right? And what you get is the difference. Okay? I guess I'll draw it like this. So that's the error, f1n. That sequence of errors are independent. So if you have an optimal predictor, your prediction errors will be independent from time to time. It sort of makes sense, because if there was a dependence between your current prediction error and your past prediction error, you would sort of use the information. The past prediction errors have exactly the same information in them as the past samples. So if the past prediction errors had some information about the current prediction error, you could use that to make the current prediction error smaller, right? And if that were true, then there would have to be information in the previous samples that would allow you to make the prediction error smaller. So it's sort of a contradiction. It's got to be the case that if you're predicting causally, the prediction errors are uncorrelated from time to time, or you haven't done the best possible job. There's some leftover information. Okay? Yeah.
But in this model, we're assuming that we're observing the values x directly, right?
Right.
So what if we're observing like a value y, which is a function of x, as the inverse problem you mentioned before?
Okay, well then that gets like, oh, well, yeah, it's a very interesting question, but well, later on we'll talk about things called hidden Markov models, where there's something similar to that, okay? And in general, if you have an operation that's not linear, then those things wouldn't be Gaussian. But if it was linear, then they'd be Gaussian, and then this would still hold true, okay? Very often, like for things like hidden Markov models, the states are discrete, so then they're definitely not Gaussian, okay? But so you have to do more complicated things. Yeah?
If you shifted one right, then the next error you predict from the next point shouldn't be independent from the previous error you just wrote down.
Feels that way,
right?
doesn't it? Okay, but it's not true. Okay. Okay. So you're saying, okay. So then what you do now? You're saying you produce this error, right? Yes. Thank you for asking that question. Okay. So you produce that error, right? And now you go and produce the next prediction error. It says that they have to be independent. Okay? So you'd say, well, why? Okay? There's a lot of reasons why. Okay? So one reason is because I proved it right here. Okay? So you have to find an error in my proof. Okay? So another reason is I can try to give you an intuitive explanation. And a third reason might be I can try to explain why your counterexample may not hold. Okay? Okay? So, I mean, so whenever you ask questions like this, right, it's like, you know, like my kids laugh, you know, why were our squirrels happy in the summertime? Okay? It's, you know, it's like, you know, happy. In order to have a real precise answer to that question, you have to define what a squirrel is, what the summertime is, and what it means to be happy. Okay? Okay? So, I mean, but you could say because it's so nice out and they're having fun. Okay? So, and like the thing is that in math, it's a funny thing. Like, you know, the correct answer to the question is, it's true because this is the theorem and I proved it. So sometimes that's not, like, satisfying at a sort of a gut level. So you try to also fill in with some kind of meaning, okay? But what does it really mean? I don't know, okay? So the meaning answer, you're going to have to forgive me, is open to interpretation as to whether you like it or not, okay? It may be satisfying to me or unsatisfying to you, but I'll try my best, okay? So, okay, first of all, okay, so let me repeat the thing I just said, because it was sort of a preemptive strike in your question, okay? Okay, sometimes hearing it twice is helpful, okay? So now you have two prediction errors, right? So what will happen is that this prediction error has to be independent of all the previous samples, okay? Because if it isn't independent of all the previous samples, you should be able to do a better job. There's a thing called the orthogonality principle, okay, which says that if you have a if you want the minimum mean square error predictor of x given y, right, that the difference between x and that times y, the expected value of this should be 0, right? That's something you learn in like 600, okay? You can prove it too. But it's an intuitive thing, which is that the error needs to be orthogonal from the information that you're using to do the prediction, because if it wasn't, you could use that information to predict better, right? In some sense, the error has to be perpendicular to the signal, okay? That makes sense, right? Okay, so this next prediction error has to be perpendicular to all the previous samples, right? But all the previous samples are a function of all the previous prediction errors. Why? Because this matrix operator here that relates x to the prediction errors has a determinant of 1, so it's invertible. So if I know the epsilons, I can calculate the x's, and if I know the x's, I can calculate the epsilon. There's a one-to-one relationship, so they carry the same information. By the way, that can be made rigorous, okay? If you really want to learn this stuff in detail, you take some rigorous probability courses, and you learn about sigma algebras, and you find out the formal meaning of what it means for two things to have the same information is that they generate the same sigma algebra.
Now,
So, if this new prediction error is independent of all the previous samples, it's got to be independent of all the previous prediction errors. QED, I'm done, right? That's sort of the hand-waving proof. Actually, what I just did in the mathematical operations sort of formalized that hand-waving proof. Okay. Now, you gave another argument, which I'm going to have trouble refuting because I don't know exactly. You kind of said, well, it feels like they should be the same, they should be related because, and I forget what came after the word.
Because 80% of your samples came from the same set that you used to predict it.
Right. Well, just because that a lot of the samples came from the same set doesn't necessarily mean that they're related, right? So, for instance, here would be an example, okay? Probably what I should do. These are really good questions, so I'm going to, you know what, I think it's more important in some ways to answer these questions than it is to explain the material, because you can go through and read the notes, okay? By the way, I'm just going to review one point, okay?
what should everybody in this class do? Read the notes.
Okay? So I can answer questions like this, okay, which are more in-depth, okay?
But,
Let's say that x, okay, x is a random vector, right? And that it has covariance r, right? Say it's a Gaussian random vector, it has covariance r, right? And then I can do an eigen, for any symmetric matrix, I can always find its eigendecomposition. I can diagonalize it with an orthonormal transform, which is to say I can write it as E transpose lambda E. We've done this already, okay, but this may or may not be, if you don't realize we've done this already in the lecture, don't feel bad, okay? Because you have to see this stuff more than once, and all of a sudden you go, oh, I see. Okay, this is diagonal matrix lambda, and the two matrices, the E and the E transpose, are orthonormal matrices, right? Okay? Uh-oh, my battery's flashing. That's fine. Oh, well, okay. I guess I just didn't worry about it. Okay, so these are two orthonormal transforms, right? Now, if I define E tilde to be equal to E transpose X, E tilde, okay, will now have the property that its autocorrelation R sub X tilde is going to be equal to lambda. Is that obvious? Maybe not. You actually had that as a homework problem, whether you realize it or not. Okay. Sometimes seeing these in a slightly different context, you feel like you've never seen it before, okay? But this is really important to understand. It's a really simple idea. And by the way, in 2D, here's the interpretation. If these are zero mean random vectors, I'm assuming this is zero mean, right? If this is X, okay, and this is X tilde, and I did a scatter plot in 2 dimensions. In 2 dimensions, in general, for a Gaussian random variable, it's distributed like a football. Not a football in Europe, a football in the United States of America, okay? Where we have oblong footballs, okay? Okay. I'm being difficult. Okay, so what happens there is that, I know, the rest of the world calls it football, but, you know, it's like, in the United States we get to have, when you win when the baseball teams all play in the World Series, they're the world champions, even though they were only basically American baseball teams and a few Canadians. Heck, you know?
The second one would be football.
Huh?
The second one would be a football.
Oh, the second one? No, it's going to be. I know where you're going. Okay, we can agree to disagree on this. Okay, so what will happen is that when I do this orthonormal transform, an orthonormal transform, if its eigenvalues are all +1, I'm not allowing, you could have -1 eigenvalues, in which case you have, a mirror reflection, okay? But let's ignore that, okay? Without loss of generality, you can always make sure that all the eigenvalues of this matrix are +1, okay? Then it's just a rigid rotation in n dimensions. So in 2 dimensions, it's a rotation of this, you can always take the football, the American football, and you can always rotate it to be aligned with the axes. So the principal axes of this ellipse are aligned with the axes of this thing, right? So what happens is that it'll then be shaped like this. And it should be the same shape if I could draw it well. It's just aligned with the axes, okay? Now, by the way, this long axis of the football is, the direction of that long axis is the principal eigenvector, and the direction of the short axis is the second eigenvector. If there's 2 dimensions, there are only 2 eigenvectors. And the width of this thing is going to be actually the square root. It's proportional to the square root of the first eigenvalue, and this is going to be proportional to the square root of the second eigenvalue, okay? So basically, this is, the eigenvalues are like the variance, okay? And the square roots are like the standard deviation, all right? So when you rotate this thing, you align it, and when you align it, you decorrelate. There's no correlation once it's aligned, right? Now, what you can also do is you could scale each of these things, and then you have a European football, okay? Okay. If you steer it, then sometimes they call it steering it, okay? Then you make it a sphere, and to do that, what you would do is you'd say, well, W should be equal to X tilde, okay, times lambda to the minus 1/2, okay? Yeah.
The first 2 equations transpose this. This should be like, it should be either E.
Do I get it backwards?
Yeah, like the E lambda E transpose. I entertain the transpose in either.
Oh, okay. I might have to transfer. I'm doing this in real time, guys. So bear with me. So I purposely put little errors in there just so that I can be sure you're on your toes. Okay. Okay. By the way, don't listen to what I say. Listen to what I mean. Okay. Now. Okay. So this is called steering the distribution. Okay. So this is a really interesting. So I wanted to point out that you took X, which was a bunch of correlated variables, and you transformed by an orthonormal transform, and you got a bunch of decorrelated variables. Okay. Now the first epsilon is generally speaking a dense matrix in say a p-dimensional space. So the first entry of X tilde is a function of all the entries of X. And the second entry of X tilde is a function of all the entries of X. They're both functions of all the entries of X, but they're independent. So that's a counterexample to your intuition. Okay? Yeah, it's good to face your fears head on. Okay? Okay. I mean, sorry to go off on a little tangent, but I think it's really important. Actually, now that you've hopefully you all ground through a lot of these complicated problems. But now you need to back up and make sure, okay, do I understand what I just did? Okay? Yeah?
I just have a follow-up question for that. Can we go back to the proof that the error and the sample are independent?
All right.
So in this, when you use the filtration property,
This proof here, this is on page 37 at the bottom, right?
yes. So in this, you use filtration property that you remove the dependence of Fn on xi.
Right.
But coming back to this question, Fn also includes some samples from before I.
Oh, okay. Fn includes samples before I, right? But now this thing here, okay, if I know everything before time n, then I know everything inside of this expression, because xi is a constant, okay? And the conditional expectation of xi given fi is also constant, and this is only a function of things before time fn too. So all these things are constant, and I can pull them out of that expectation. Is that what your question was?
I was just trying to relate what you said to the theoretical proof over here, and just trying to find if that sort of dependence on previous samples could relate to something here.
Well, I'm reluctant to go into. I mean, I think you can stare at this thing and then can draw that analogy in your own mind. But in a sense, at least to some degree, it's a personal thing. Okay, because what makes you feel like it's compelling intuitively might be a little different than what makes me feel that way. Okay, I'm giving you some different ways of thinking about it that can help you get intuition into the problem, right? Is that good? Yes. So, okay, so now, okay, good. So the important thing here is that the key issue here is that the prediction errors are independent, okay?
There's two key issues, actually.
The prediction errors are independent, okay? So let me zoom out.
Okay. First, the prediction errors are IID, are
Independent.
okay? They're independent, so
This thing is epsilon n is independent of epsilon I for n not equal to I, right? And that a times x equals epsilon, where the determinant of a equals 1. Okay. Now, I'm going to make some simplifications, I think, to keep things from getting too complicated. Okay, so the expected value of epsilon transpose is it's going to be these are going to be independent. So that has to be a matrix which is lambda, which is diagonal. Okay, with some kind of element, and they can't be 0. Okay. Why can't they be 0? Because I may be, well, partly for a technical reason, a little bit silly. It's okay, which is, I assume that the random process is jointly Gaussian. And I made a hidden technical assumption just to avoid bad problems. It's a little bit, I'm being a little bit underhanded here, okay? Okay, because in my definition of jointly Gaussian random processes, I do not allow for the possibility that the eigenvalue is 0, okay? So you can't have a singular covariance matrix, okay? I just assumed that because I don't have to deal with it, okay? Yeah.
So you can't have a Gaussian with 0 variance, can you?
Well, I mean, it's like, we can also discuss how many angels can dance on the head of a pin. I want to avoid that problem because it creates a lot of technical difficulties, but in some application, it could be that you have some Gaussian random variables and that some linear combination of them is that they're linearly dependent, okay? That's essentially what it means. So that there's some dimension in which their linear combination is 0, okay? A simple way to do that, okay, I hate to go off on a tangent, but okay, let me give you an example that, like, confirms your worst nightmares, okay? Which is you had two independent random variables, x1 and x2, right? And you said that, well, x3 is going to be equal to 1/2 x1 plus 1/2 x2, right? Then, according to my definition, the vector x1, x2, and x3 is not a Gaussian random vector. Okay, which is like maybe unsatisfying, okay? But each is a Gaussian random vector, right? And they're pairwise Gaussian random vectors. But according to because the determinant of the covariance will be a single eigenvalue. Because one variable is just a linear function of the other. Okay? Essentially, but I'm just making that assumption to keep, for lots of reasons. Because then, if I define this as a Gaussian random vector, then I have to allow for the possibility of Gaussian random variables whose variance is 0. Okay, and then it's not a random variable with a density function. It's a deterministic random variable, right?
So my intuition was that the eigenvalues were the magnitude of the eigenvector was the variance of that dimension of the...
Yes, that's correct.
Okay, so that means if you have a 0 eigenvector, there's no variance.
That's correct.
All the variances in x1 and x2 and x3
Correct.
have no variance.
So for instance, let's say I'll make it a simpler problem, because in 3D I have trouble drawing three-dimensional graphs, okay? So if I say x1 equals x2, okay, then you have perfect correlation. Then the distribution looks like this, straight line, okay? So its variance along the thin axis has width 0. I say that's not, I don't allow that possibility, because I said that all covariance matrices have to have eigenvalues, have to have the non-zero determinant. Okay. Sorry. I actually went back and forth on that, but I decided it was better to just get rid of that nasty case. Okay? So anyway, so here this matrix has to be diagonal with non-zero entries, strictly positive entries, okay? Okay, now, so I can write down this distribution. So P epsilon of epsilon, the probability distribution for epsilon, I can write down. It's just going to be equal to 1 over 2 pi, okay, to the, say, P over 2, right, times, now this would be lambda, right? Lambda is the covariance, so I'll take the determinant of that to the minus 1/2, right, times the exponential of minus 1/2, and then it'll just be the norm of epsilon squared. Everybody should be able to write that distribution down very quickly, right? This has to be the distribution of epsilon, because epsilon is Gaussian, and each of its elements is independent, and they each have, I'm sorry, this is wrong, okay? I forgot. Yes, I have epsilon here, where I'm defining the norm of epsilon squared with the subscript of epsilon, the subscript of lambda to be equal to epsilon transpose lambda epsilon, okay? So that's like a weighted L2 norm.
Lambda inverse, right?
Lambda inverse, yes. Okay? So it's lambda inverse. So, yeah, I should put it inverse here, okay? So I have a closed form expression for the distribution of epsilon, right? Now, in addition, I know that x is equal to A inverse of epsilon. Because A has to be an invertible matrix because the determinant is 1. So I can write down the distribution of this thing. The distribution of this thing is epsilon as a distribution of, the distribution of x, right, is got to be equal to the distribution of epsilon with A inverse of epsilon plugged into the, of x,
It's smaller.
Okay, let me start all over again because I'm messing this up. You know, guys, okay. It's the distribution of x, right, has got to be equal to the distribution of epsilon, where I wouldn't want to plug epsilon in here, but I don't have epsilon, I have x. So then I take A times x, right? And now I have to multiply by the Jacobian of the transformation. But the Jacobian of the transformation, or the inverse of the Jacobian, one of those two. But it doesn't matter, because the Jacobian of the transformation is 1. Okay? So it's going to be the determinant of A, or 1 over the determinant of A. Does anybody know what is A or Okay. Okay. I'll leave that as a homework assignment. Okay? But the bottom line is, it's 1. Huh? Oh, it's inverse? Okay, good. Inverse, okay? Either way, it's 1, okay? So the beauty of the thing is that if you have a causal predictor, the determinant of the transform is 1 by virtue of the fact that it's a causal predictor. Because why is this determinant 1? It's determinant 1 because, if you go back here, the matrix was lower triangular with 1s on the diagonal. It was lower triangular because it's a causal predictor, and it has 1s on the diagonal because you always have to subtract the estimate from the current value, right? So, you can write down the distribution in closed form. When you do that, all this, you know what we're going to learn later in the class. I'm going to stop bothering to write this normalizing constant down, okay? Because you can always write it down later. So you can always figure out what that normalizing constant in the distribution has to be, okay? So I'll just, to save time, I'll write 1 over z, okay? Because it's faster. And then I say, oh, well, this will be the exponential, and it'll be minus 1/2, and now for epsilon, I plug in AX. So I get here X transpose A transpose lambda inverse AX. So now I've written down the distribution for x. So, okay, coming back to the original point, I was able to write down the distribution of the random process x by using a model based upon a causal predictor. By predicting, so to write down the distribution is to model, in my book. Modeling is writing down the distribution, or at least one way of modeling is to write down the distribution. Because if I know the distribution of something, I have a model for it, right? So, I was able to model the distribution of this x by first starting off by defining a predictor. Remember my original point was, if you can predict something, you can describe it. Okay? You know it. You can model it. If you can predict your parents, you must know them well. Okay? You know them well because you can predict them. It's sort of one and the same thing. Prediction and understanding something are very closely related. Okay? So, okay, now what I want to do is I say, okay, well, now this is all well and fine and good, and it's a little bit general, but we can make it a little more specific. In practice, you would need these coefficients, these h's, of this lower triangular matrix. You would use them to actually predict each value, right? And in general, these coefficients could be, you know, well, I don't want to say anything because they really can't be anything, but they can be a lot of stuff. Okay, I mean, there's a lot of possible matrices that could reasonably be used to predict the next value. But now what would happen is that, let's say you have a signal of length 1,000. Okay, you would need a 1,000 by 1,000 matrix. Now, you don't need all the entries, but you need most of them. So you need, basically, if it's a P by P matrix, you can take P squared minus P over 2. Because there's P squared entries in the matrix, there's P along the diagonal, so if you subtract off the P along the diagonal, of the remaining, you need half of those. So this is how many entries you need to know. So you need know a lot of entries. So these are all unknown parameters, and estimating those parameters is hard. So in general, one of the major themes of the course is to reduce the number of parameters you have to estimate. So you don't have to estimate these parameters. So what are you going to do? You have to make some sort of simplifying assumption. So the simplifying assumption that people make typically is they assume that the random process is stationary, so that the prediction filter is not a function of time. Then it becomes just convolution. The minimum mean square error predictor becomes convolution, and that's what is called an autoregressive process. An autoregressive process in 1D, okay? In that case, then the predictor is formed by 2-minute warning that we have a filter applied to x, okay? And it's a linear time invariant filter, so it's convolution. So you can do it in the frequency domain, in fact. And then the prediction error is also a linear filter, but the only difference is that linear filter has an impulse response which has a causal impulse response, but its value at time 0 is 1, right? I mean, and the matrix, then the matrix is totalist. Totalist is a very important concept. Totalist, you got to read this, because I'm going to explain it takes too long. But it's very important. If the matrix is totalist, it means that each row of the matrix is formed by a shifted version of the same signal. If it actually shifts around in a circle, then you call it circulant. If it's circulant, then you can do circulant operations with FFTs. But if it's not circulant, but it's truncation, you can't do it with an FFT. Well, you can, but you have to do like overlap state kinds of things. Okay. But so this is totalist and circulant matrices will play a very important role in what we do, and there's a cool homework question you're going to really hate. Okay. But anyway, on that problem, and then okay, so then you can look at the power spectrum of the resulting signal, and it has this following form, where H is the Fourier transform of the whatchamacallit. Okay, we need to switch back because I only have 30 seconds. Okay. Okay, how come it's not switching back? Oh, there we go. Okay, because I want to say goodbye. Okay, so, what are we taking away from this? The first thing is you have to remember, read the notes. Okay? Then, do the homework. If you can't do all the problems, do the ones you can, okay? And try to understand the concepts. That's the most important thing. And causal prediction can be used to model signals.